All right, lecture 19, we're going to learn how to draw Lewis structures. Change your world kind of day. And announcements, you just have homework on OWL lecture 19. I'm going to say it now, and I'm going to give you a little sermon at the end of the class too. I'm going to teach you how to draw things. You need to do that for your homework. You need to write things on a piece of paper. That's how you do well in this class. If you do it in your head, you're going to get lost and things are going to get messed up. Listen to me, PhD, I've been doing chemistry 30 years. I still write things out. I do not do it in my head. If you're doing it in your head, you're doing it wrong. You will get lost and you'll make mistakes, okay? So we're going to learn how to do Lewis structures. I'm going to give you some rules, and you need to practice them in your little OWL notebook that I hope that you have with you. And then you'll just start having a bunch of these structures. We're going to do structures, lots of them, all next week. And so it'd be great if you could start just keeping a big list of them. And then you're like, oh yeah, I see it here, I see it here. And Lewis structures will become very familiar to you. Lab number 4 is on Monday. There's really no math really to speak of for Monday, so this is great. But you're going to learn how to do chromatography. Chromatography is a word that I don't think anyone else uses, at least how we use it. Chromatography means separations. Chemistry is messy. If you ever get the chance to do some synthesis to make new molecules, you will find out it's super messy. I did a bunch of synthesis when I was in grad school. I spent most of my time cleaning up the mess. And I'm not talking wiping down tables. I'm talking about I've got all these chemicals, thousands of different types, and there's one that I need in there. How do I separate them? That's what you guys are going to do. We're going to give you a mixture of red, blue, and yellow food colorings, and you're going to be able to separate them right back into their components. Completely red, completely blue, completely yellow. That's what chemistry does. That's what chromatography is about. And one of the key ways to do that is to use polarity, that concept that we're learning about with the polar and nonpolar molecules, bonds, and that will extend to the molecules. So that's going to be the big theme there. And we're making our way through the exams. Everyone's got a ton of stuff going on, but we'll have them back to you on Monday in the mailbox out in the hallway. All right, so big day, Lewis structures. This is going to change your world here. Okay, and then everything I just put up on the board is there on the screen so you can get this. All right, so we're going to learn how to draw molecules and polyatomic ions. Does anybody know what the word poly means? Many. What does atomic mean? Atoms. So many atoms together as one ion. That's what we mean polyatomic. Let me give you an example. One that we're going to learn to draw today is the carbonate molecule. It's carbon and there's some oxygens around it. And we're going to learn that some different things about it and how to draw it. And this is going to be its structure right here. And we're going to learn how to put all the dots and all the lines and all the brackets and all the numbers. We're going to learn all that. But that's a polyatomic ion. Now, what can you tell me about the type of atoms that are in here? Is oxygen a metal or non-metal? How about carbon? So these are going to be covalently, they're weird. They have covalent bonds in it, but the entire thing is an ion. And there's a big list of these you're going to memorize, their names, and then you're going to know how to draw the structures by the end of next week. And then lab number 5, you guys are going to be building them with little molecules kits in lab. Okay? And so if you are avoiding the names in the drawing of the structures, you're going to be in trouble. So we want to embrace it and start learning their names and their structures and stuff. And that's really what our next week is all about. And these are going to be the characters in our chemical drama, if you will, for the rest of the year. All right, so Lewis structures of covalent molecules. So we're going to be drawing them of those systems that are just nonmetals. We're going to be basically in that upper right-hand part of the periodic table. Now, these molecules, there's going to be like some driving force that we're going to be looking for. And it's 2 things. Some molecules want to have 2 electrons in their outer orbitals, okay? And some want to have, if you're sharing them, we learned how to share them, and some want to have 8. Now, where does this 8 number, so 8 is like a stable number. Where do you think that number 8 comes from? I know the s electrons want to have 2, but that's not 8. The p electrons want to have 6, but that's not 8. So where does 8 come from? How about you just add them together? 2 plus 6, right? That's where you get 8. So there is stability when these atoms have their s and the p orbitals full. Now, hydrogen and helium don't get the opportunity to fill up any p orbitals. So they're going to be stable with 2 electrons. So that's going to be called the duet identity there, the duet rule. Hydrogen just wants 1 more electron because it comes with 1, wants 1 more. That's it, doesn't need anything else. Now in that row 2 and row 3 and 4, these guys want to have 8 electrons. And we're going to learn that there is a way to get to 8. You can use these electrons that are on the outside, and then it will also count the ones that are on the bonds. And we'll go over this a number of times. So this oxygen is going to be stable because it has 2 of these, 4, 6, and 8. So when you see a bond, both oxygens can count the electrons. So this oxygen, 2, 4, 6, and 8, it will also get to count the bonds just like if it was fully their own. That's what's so great about sharing and what that line means when you draw a bond. Now, we're going to learn how to do all that with some sample molecules. But in order to draw them, we need to decide what are the electrons in the valence. And so valence electrons are the electrons on the outside of the noble gas core. You can quickly identify them by understanding what group it's in. So lithium, beryllium, 1, 2, they're looking at the A part, 3A, 4A, 5. That's why I had a hand draw. Sorry, you can see my hand drawing in there. 3, 4, 5, 6, 7, and 8. And looking there, it corresponds directly to the number of valence electrons. Now, don't worry about the dots and how the number of dots and stuff that are around the atoms, but that's how sometimes people do it. And you can see the electron configurations there along that group, S2 and P3, P4, P5, P6. So you can see the electron configuration. And if you're in the same group, you're going to have the same number of valence electrons as the other people in your group. So let's go ahead and see if we can figure this out with a few practice ones and see if you understood what I was just saying. And so let's bring this back up and we'll do a poll, but a numeric poll. How many valence electrons, let's go to numeric. How many valence electrons does oxygen have? And give me a second, I'll pull this up. Feel free to talk with each other and try to remember what I just said. Okay, we're not going to take a long time, so I hope you guys are paying attention here. If you're not sure, just put in a number. Do your best. And we'll do all of them. Hopefully we'll get very fast at this. This is not something that should take more than 10, 15 seconds when we get it figured out. But until then, it may take a little longer. All right, let's see what you guys got in 3, 2, 1, and 0. Remember, if you're not clicking in, you're not getting attendance credit. So, all right. We've got most people picking 6. That's correct. How did you guys figure that out? How did you guys figure it out with 6? It's in 6A. Great. All right, let's do it for nitrogen. Let's see if we can get everybody on board here. Okay, let's see if we can do it for nitrogen. Okay, how many valence electrons does nitrogen have? So for oxygen, we went to oxygen and we looked and we said it was 6A. So let's look at nitrogen. It's in 5A. Okay, we're going to take 30 seconds and then we'll start doing it faster and faster. All right, in 5 seconds, 4, 3, 2, 1, and 0. Okay, very good. Yay! Okay, now I'm not going to say anything. Okay, let's do chlorine. Okay, chlorine. 20 seconds. 10 more seconds. All right, 3, 2, 1, and 0. Okay, well, chlorine was 7. Very good. So I'm sorry, I'm not sure where you got 4 from, but let me point it out again. So chlorine is right here, and it's in group 17, but it's also in 7A, so these all have 7. Okay, maybe it was a typo. All right. All right, actually, just let's just yell out some of these, and then we'll pause and we'll type in. Okay, there's chlorine. What's sulfur? We had it up here too. 6. All right. What about iodine? 7. Okay, don't say this one. Type it in. We're going to do krypton now as a numeric one. This one's a bit tricky, but follow the words that I've been saying. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Good. All right. Yeah, I thought I counted 19. Okay. How many for krypton? We'll give you a few more seconds here. You got to pick a number. You got to go with something, and then we'll straighten it out if it's not right. All right. 3, 2, 1, and 0. Just pick something. It's okay. Nope. Pick something. There's 18 of you guys. All right, thank you. It's okay to be wrong. We want to understand. Okay, so the answer is 8, and let's see where that comes from. Okay, I see we got some different numbers, and 0 is like a possibility because you could say it's full. So even for these noble gases right here, we're just going to go with group 8A. We'll use all 8 electrons. Okay? So let's use 8. It's okay to be wrong, you guys. We just want to make it and get better at it. So those are, is there a question on it? So any noble gas is 8. What about carbon? Yell it out. Boron. 3. Questions? Because everything's going to start getting faster and faster. This is easy. I'm not going to ask this kind of stuff again. We're just going to start adding numbers together. Because we're going to start putting systems together, and we're going to go, yeah, and these numbers never change, you guys. You don't have to worry about it going, well, tomorrow it's 8 or 3 or whatever. I mean, it's always the same. All right. Gilbert Lewis is a scientist, chemist here, who used electrons to figure out structures and relationships in molecules. In fact, his name is synonymous. That means it's the same as the word, to me, electron. So he tried to explain a lot of things using electrons, and he was right on a lot of it. So the method we're going to do is his method, but it's been modified through the years to be very efficient and to work well on a wide variety of molecules if you follow the rules. So this might not have been the exact way that he did it, but we have some really good ways. How many people have drawn Lewis structures in high school or before? Okay. Now I'm going to ask you if you've done it my way at the end, because you're doing it my way now, okay? You're not going to do it your way if it's different. If your way and my way were the same, woohoo, great. God bless your teachers. They're getting the message. Because this way works really well, and it works for a wide variety of molecules. So when you hear Lewis, I want you guys to start thinking electrons. In fact, you should say it. So if you hear Lewis, you think what? From the rest of your life. So there are Lewis acid bases. That means they use electrons to figure that out. Lewis structures. I'm trying to think. There's something else. It's got to be, because this guy loved electrons, and it works well. Most college textbooks are teaching this way. We need to get it into our high schools. A lot of them are doing it this way, and they need to be doing it this way. There's 2 ways to find electrons. Electrons want to come in pairs. Why do electrons want to come in pairs? You know what pair means 2, right? Right? Okay. Right? Because all the animals that went in the ark went in pairs, right? Groups of 2, except for the worms. Right? They went in apples. Okay. All right. So 2 types of pairs of electrons. Not those kind of pairs. We have a lot of those pairs around here. There are lone pairs, which are going to look like if this was oxygen right here. They're going to be by themselves. And this is going to be called a lone pair, LP. And sometimes I may ask you how many lone pairs, and then you start counting in twos. Okay? So that would be one lone pair. This would be a second lone pair. And then sometimes I may want to know, and in fact, that's what we're going to do today, how many lone pair electrons are there? Then you just start counting all of the dots. 1, 2, 3, 4. So that is a type of, so it's localized into a lone pair. This is why it's called the localized electron model. Or the electrons could come in bonding pairs. Wait, did we explain why they like to come in pairs of 2? Orbitals, right? MS plus 1, half. So we got up, down. That's what we got going on here. Bonding pairs. Bonding means 2 electrons, but they're being shared. And so that's one bonding pair, 2 bonding pairs, and then sometimes I may ask you how many electrons. In fact, that's what we're going to do today, bonding pair electrons. So as another example, here's hydrogen chloride. I drew the structure out. We'll learn how to draw it later on. But just if it was given to you, I have 1 bonding pair electron and bonding pair and 3 lone pairs. But I have 2 bonding pair electrons, and they're being shared, and I have 6 lone pair electrons. So you got to be paying attention as you're reading. Is he asking for the pairs or is he asking for the electrons? And if it's not clear, you just ask, okay? And Dr. Hayes, was that with pairs or number of electrons? Okay. And I'll try to be clear in the question because I know that this is a point of confusion that we want to know what to do. All right. Now, hydrogen, as we just said, already wants to form a stable molecule where it has 2 electrons that it can get from sharing. This is one of the simplest molecules, is hydrogen. And that bond right there represents 2 electrons, and each hydrogen can count it towards its duet. Duet means 2. And so it just has its 2 electrons. It's happy. It's done. And actually, because of that, hydrogens will never have double or triple bonds. This will never happen. Hydrogens will always have single bonds to them. If you draw a double bond to hydrogen, you did something wrong. If you draw a triple bond, you did something really wrong. It's tiny. If we could just see it and try to put electrons on it, you could say, man, I tried to put more on there and they just fall right off. It doesn't happen. You don't have to worry about that. This is what you learn by coming into class and you paying attention and you're writing stuff down, that hydrogen will never have 2 and 3 bonds. If you're doing it, you're doing something wrong. And you go back and you start over and you think about what's going on there. All right. Now, all the other atoms besides hydrogen and helium, though, we don't see too much or at all because it doesn't like to make molecules. Don't worry about how I've drawn things up here. What I want to show you is that the rest of the molecules want to get to an octet. They want to have 8 for stability. And the way that they get to 8 is that they get to count bonding and the lone pairs together. And when they do that, that adds up to 8. So both fluorines have 8 electrons around it. 1 bonding pair and 3 lone pairs, but 6 lone pair of electrons altogether there. And I'll do a better job. 6 altogether. 6 lone pairs. 6 lone pairs. 1, 2, 3, 4, 5, 6. All right. But 3 around each fluorine. So the idea is octet rule is they want to have 8. That's my main thing I want to point at. All right, some other nomenclature before we get too far. If you see a single bond, we'll sometimes call that a bond order of 1. And this is not tricky here. Double bonds are called bond order of 2. Triple bonds, which you may see in some atoms or molecules, have bond order of 3. Later on, next week, we're going to encounter situations where we might see something that has bond order of 1.5 or 1.67. 1 2/3, 1 1/3. Okay? And then you're going to say, oh, then it must be somewhere in between a single and double bond. Okay. Now I'm going to show you this 7 steps for writing Lewis structures. And as the great coach Vince Lombardi from the Green Bay Packers, he's a great coach, Green Bay Packers, not a big fan, although you got to give them some credit for all their winning that they do at the expense of the Detroit Lions, my team. So he had this practice makes perfect. Doing it this way that I'm going to show you is what you need to do. Okay? But my teacher in high school told me a different way. Well, if it's different than my way, then you got to erase that from your head. And you have to do it this way. And I'm going to show you all the steps. So what you want to do is you want to get faster at them, okay, at the steps. I'm not joking, you guys, because I'll take points off if you don't do it this way. Now, when you're practicing this weekend, I won't be there taking points off, but you want to be drawing it in your OWL notebooks. All right, we're going to draw 3 molecules here this morning. Water, and it's going to highlight a number of rules. It won't highlight all of them, but we got to get started somewhere. Boron trifluoride and that carbonate that we were talking about. This will highlight a number of the situations right here. So we start your Lewis structure journey with these 3. And we're going to do many, many more. And here's how it goes. Step number, well, these are the 7 steps. Draw structures for these molecules or ions so that they each have octets unless it's a hydrogen. Then it'll be a duet. And this is my little reminder page up here. So we're going to go on to our first rule, though. First rule. First thing you want to do is count up all of the available electrons from each atom. So that's why we did that counting before. So let's do the total valence electrons. So you want to start doing this now. You'll be doing it on paper here. You'll be doing it with your OWL homework this weekend. Nobody will be watching you. But what you do in secret there, we'll know later on if you're not doing it because you'll forget. Okay, what does it say? Total valence, add all the valence electrons together from each atom. How many valence electrons for hydrogen? 1. But how many hydrogens do I have? 2. Okay, so I'll write it like this. 2 hydrogens that have 1 valence electron, so 2 times 1. And then how many valence electrons does oxygen have? 6. Okay, if you're looking at this periodic table, you just look at the number there at the end. Okay, that's why we did all of that. So what is the total when you add them all together? 8. Okay, so let's go over here. Total valence electrons. Now, if you can just put that in there, but I often write this out so that I can remember where it came from, and we can see how people came up with it. How many valence electrons for boron? 3. Okay. Now I have 3 fluorines. Remember, this is what we were learning yesterday, that the subscript down to the bottom right refers back up. So that's how many atoms I have. All right. How many valence electrons does fluorine have? 7. What's the total? That's 21 plus 3 is 24 altogether. Let's go over here. Total valence electrons. Carbon has how many? 4. How many does oxygen have? 6, but there's 3 oxygens right there. See, there's 3 O's. And then, so that's 6. Now, let's read some of these other ones. So it says group number of the elements is the valence electrons that we were practicing. And then the third bullet point, add electrons for negatively charged ions. Is this a positively charged ion or a negatively charged? Negative, good. So the way you remember this is that, okay, I have a negative 2 charge. That means there was extra, so you add 2 electrons. If you had a cation listed there, okay, so we will tell you, like, hey, this is a cation. You will then subtract from the total. So we have extra electrons, we've got to add it. So what's my total number now? That's 18, plus 2 is 20, plus 4 is 24. All right, so we're going to have these little tallies of electrons on the side. You need to be doing that. I still do it. And I'm chemistry 30 years, doing Lewis structures for kids, students here, 15 years, and I still do it because it's a way to make sure I'm doing them right. If I am doing that, and the teacher is saying, you must do it, or you'll get things wrong and you'll lose points, that means you must be doing it. All right, so if you have questions like, well, where did you get that? Please be asking. Okay, step 2. Step 2 is to draw a skeletal structure with single bonds to from a middle atom to the others. There's a couple of rules that we got to learn here. Okay, well, who's going to go in the middle? The middle one is usually the lowest electronegativity, the most metallic, the thing that's to the left on the periodic table, whatever way you want to think of it. That's why we're learning those electronegativity numbers. Okay, except we're going to run into situations like with water. Hydrogen is going to be on a terminal atom. Terminal atoms are on the outside. So to resolve this, okay, our goal here is to draw a single bond to connect the central atom to the terminal atoms. So we really only have one choice here to put oxygen in the middle and hydrogen's on the outside, because if I put hydrogen in the middle, you're going to do something like this, and that is wrong. Why is that wrong? How many bonds does hydrogen have? 2. You say, but that doesn't look like that up there. Well, maybe I need to add the... Okay, so whether it's 2 bonds that way or whether hydrogen has 2 bonds that way is still wrong. It's too many electrons for hydrogen. It won't happen. So we can't put hydrogen in here because we've got to hold them together somehow. And the only way to do that is to put the most electronegative. So right away we violate that one rule. And anyway, so we're done with this step. Okay. Oh, no, we're not. BPE. Okay, I've used up some of the electrons with the bonds. How many did I use up in the bonds? 2, 4. Okay, let's go over here to boron trifluoride. Who is the least electronegative? Boron or fluorine? Who's the least? Boron. You guys memorized that fluorine was the most electronegative. So he's going to end up on the outside. Oxygen is the second most electronegative. You're going to see that they end up on the outside as well. So we put boron in the middle, and you put fluorine around the outside. And don't worry about bond angles and all that stuff. We'll do that next week. Just connect them. Single bond, connect to the inner to the outer atoms, the terminals. So these are called terminal atoms. The fluorines are the terminal ones. Boron's in the middle. Oxygen's the middle, the central. Okay, so maybe we need to highlight that. Central. And then all the fluorines are the terminals. Okay, those are the terminals. So we're going to use that nomenclature, those words a lot. Central and terminal. Central, because a lot of these are like, that we're going to be dealing with are something in the middle and then stuff on the outside, terminal position. Who goes in the middle over here? Carbon or oxygen? How do you know? Least electronegative. Okay, we're just following the rules, except for we're going to run into some rough situations sometime. So just put the oxygens around. Don't worry about, they just one bond, connect them, and this is the skeletal structure. We're going to build on top of it, just like your body is built on top of a skeleton. Okay, now what we didn't do over here was the bonding pair electrons. Okay, how many electrons are in the bonding pairs? 6. What about over here for carbonate? 6 as well. So what we're doing is we have a total number of electrons. We're starting to use them up. So we're going to put some in the bonds. Bonding pair electrons. So we add them all up, call it the bonding pair electrons. Step 3. Step 3, we're going to start thinking about the terminal atoms, which is the hydrogens here, the fluorines here, and the oxygens. Our next steps after that, we'll think about the central one. Let's ignore this central one right now. Place the lone pairs of electrons about each terminal atom to complete their octets or duets. Now, hydrogen is done. There's nothing to put here. So we don't do anything for that step. But I want to tally it, because at the bottom it says count all the lone pair of electrons on the terminal atoms. So I'm not going to put any electrons around the outside because it's done. So what should I write here for this number? Well, I'm going to put 0. Okay, because I didn't put anything there. Now for the lone pairs here, what we're going to do is complete the octet. It says hydrogen can only have 2 electrons, no LPEs, no lone pair electrons for hydrogens. Usually add 3 pairs of electrons to all the terminal atoms. So what does that mean? So these fluorines were the terminal ones. We're just going to go dot, 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 dot. That we're putting 6 there, and that will add with the 2 bonding electrons to give us 8. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So how many lone pair electrons did I put on the terminal? I'm only worried about the terminal ones with this step. How many electrons did I just put down altogether? 18. Good. And we do the same thing over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So basically you're going to put 6 unless you're dealing with hydrogen, then you don't put any. Okay? Now, how many lone pairs did I use here? 6, 6, 6. How many? 18 altogether. Okay. Now, our next step is to tally them all by taking the total and subtracting the bounding pair, subtracting how many you put on the lone pair. We're going to subtract them, and then we're going to figure out how many electrons remain, and this will tell us exactly what we need to do with the central atom. So let's figure out how many remain. So if I started with 8 and I use 4 here and I don't use any here, how many do I have left over? 8 minus 4 minus 0. What does that equal, you guys? Okay, we're losing you already. Sorry. 24 minus 8 minus 18, what do we have? 24 minus 6 minus 18. 0. Okay. How many over here? 24 minus 6 minus 18. 0. Am I losing you guys? Or is that just, do you need a calculator? I don't know. Yeah, if you just use a calculator if you're not sure. But hopefully we can do the subtraction in our heads. All right. Tally. So this is 4th step. Not too bad. Now, what do we do with it? That's 5th step. Now we're going to look at the remaining numbers. If Re, the remaining electrons, if there are, the bold letters, if there are more electrons left, that's remaining, put them on the central atom. That's how I know what to put on the central atom. I don't look it up on the internet. I don't look at others' examples. I follow the rules, and that tells me what to do next. Okay? So how many electrons do I have here for water? I have 4. So and it says, up there in the box, it says put them in pairs and try to spread them out. Okay? 2, 4. I knew to put 4 dots because of this number right here. So I use them up and I put them on the central atom. Okay, let's go over here. I have an RE of 0. So how many dots do I put on here? None. Okay, I had 4 here, so I put 4 here. The RE says 0, so I don't put any dots. The method tells you what to do. So we go over here. This is for the central atom. Maybe we should put a C for central and T for terminals. I'm thinking about adding that there because students get confused and they weren't paying attention. Okay, so the LPEs are for the terminals. The RE is really the lone pairs that go on the central. So how many do you put on that carbon? 0. The method told me. You don't have to worry about, well, what does the internet say? The internet could be wrong. Okay, so we'll just follow. All right, sometimes you get so many remaining electrons, it will push it beyond the octet. This can happen, and it will happen once in a while, for things in the 3rd row. Who's the 3rd row? Phosphorus, sulfur, chlorine. Okay? They can have expanded octets. The group 2, right here, row 2, they will never have expanded octets. Boron, carbon, nitrogen, because they're too small. They don't have extra orbitals for that. Remember, and if you're in the third Boers Hotel, and you've used up your hotel rooms in the S and P, and you're on the 3rd floor, there's extra rooms. Where are they? 3P, 3S, 3P, 3D. So these guys can access the 3D orbitals and put some extra electrons because they're on the 3rd floor. Okay? These guys, that 3rd floor is too far away. 3rd floor is too far away. So they will not exceed the octet rule. On this next slide, I give you some examples of exceeded octets, like the xenon. Yes, they made compounds with xenon, but it used very electronegative. Xenon here has 2, 4, 6, 8, 10. 12. 2, 4, 6, 8, 10. 12 electrons are on there. So does that iodine right there. It happens sometimes. There's another example of an expanded octet. All right. That's central atom. If the central atom has an incomplete octet, use electrons from the terminal atoms to make double or triple bonds. Okay. I think I'll start down here and do that because it's going to get confusing if we go this way. Okay. It says move a lone pair from a terminal atom. Those are the ones here on the outside. And we're going to move them into the bond and make a bond. Don't split up lone pairs. You can't just take one. You got to take them both. And you're going to move 2 electrons at a time. So I'm going to take 2 electrons, and it doesn't matter which oxygen I take them from, but I'm going to make them into a bond. So I've moved 2 into this bond right here. Stop drawing multiple bonds when the octet is reached for the central atom. Let's take a look here. 2, 4, 6, 8. Yep, I now have 8 electrons. They're all in bonds around the carbon. I'm done. In fact, that structure is essentially done. So that's how we figure out if there's double or triple bonds. Okay? Don't look this stuff up on the internet right here, because you may, some of these you'll find, oh, that looks good. The internet tells me. And then you're going to see sometimes they're like, whoa, where did all those bonds come from? I'll explain it all next week. You got to do it this way. And this will answer most of your questions. Okay? All right. Carbons, which we've seen here, oxygens, nitrogens, phosphorus, they like to form multiple bonds. This rule right here we're going to run into. Terminal halogens do not form multiple bonds. They really just want to, these just need one more electron. These just need one more electron. So they will not form double bonds. What does that mean? Well, right here, see boron, 246, would love to have one more bond. And it would make sense for us to kind of move one of those into here. And we're gonna prove why this is not allowed next week, but you're gonna have to trust me for now. This is not allowed. I cannot put a bond there. I've got to leave this in the terminal atom position. This puts boron in a very precarious position because I have run out of electrons. They're all in lone pairs or they're in bonds. What am I supposed to do? And the answer is nothing. You're done. Boron violates, and it's a well-known violator of the octet rule. That's why I'm showing it to you. And it kind of makes sense if you think about it, because boron is only bringing 3 electrons to the structure. So it can't provide all the ones that even carbon can. Carbon, with its 1 extra electron, and it got a few extra from a metal, because that's where electrons come from. They come from metals. And it picked up a few extra electrons, and so that was able to complete the octet there. All right, we come over here, and octet and duet rule is met. This one's done. We don't do any double bonds because everything's good here. 2, 4, 6, 8, and this is done as well. And this one is done. However, this is an ion, and the way that we designate ions so that we can tell them is we're going to put brackets around it. We'll put brackets around it in the upper right-hand corner. We'll put the charge, -2 charge, up there. Now it's done. Now it's done. If there's an odd number of electrons, sometimes when you do this right here, you're going to end up with an odd number. You still put it on there. Okay? Whatever number you get, that's what you put on the central atom. Even if it looks weird, that's what you do. Okay? Boron and beryllium just don't have enough electrons to go around and they often have incomplete octets. That's well known. There are some times, and I'll give you an example up here in the upper right-hand corner, this nitrogen dioxide has an odd number of electrons, which is weird. If you see odd numbers, something might be going on. You got to double check that you're doing everything all right. And that is the correct thing. So this is the correct structure for nitrogen dioxide. It only has 7 around the nitrogen. Actually, this becomes very powerful because boron, we'd say, man, it really wants an octet. Yep, that compound is really reactive because it wants 2 more electrons. And so it's seeking another molecule to steal them from and cause a chemical reaction and take them. So we would predict that this is a reactive molecule because of the incomplete octet, and that is true. We also have a similar prediction for nitrogen dioxide because it is missing an electron. It would be reactive, and it is. Very reactive. In fact, that's called a radical reaction, and it does a lot of amazing things. So it's very important. And we got there because it had an odd number of total valence electrons. Next week, we're going to learn how to draw better structures. These structures I will designate by the phrase meets the octet rule. Because that's what we were doing. We were trying to meet the octet rule. There are known violators that will exceed it, like sulfur hexafluoride. You're going to go over the fluoride, and that's okay because sulfur is in the middle. So in your OWL homework, you need to be drawing this out in your papers. Don't short circuit this for yourself. Like we were learning how to write units last week, when you stopped writing units, you were missing out on an opportunity, because units help with here. And this process works really well. How many people did this process in high school? Oh, good. Oh, many more of you guys here. Okay. If you didn't, yeah, that's okay. I'm teaching it to you. So I never did that before. We're doing it now. Learn it. Okay? Well, I did it some other way. Then you have to unlearn that way. And you have to do it my way. Okay? And there's meanings behind each one of these. I thought I had somewhere in here. Anyway, when you get done, it is somewhere in here. Don't go back. Like I went back and I changed how many bonding pairs, how many lone pairs. Do not go back and change those numbers. Did they change how many lone pairs and remaining? Yep. But that's not what this is about. This is an accounting system for how to build the molecule. Don't go back and change it. Now, I can ask you after you built it correctly, hey, how many bonding pair electrons did you have? Well, that would give you the wrong answer for the molecule, but don't change those. Okay, this is for building the molecule, because when I go and help you, and I'll say, well, how many bonding pair electrons you had? Well, I had 8. Well, then you did it wrong. Well, I had 8 at the end. No, how many did you have when you were building the structure? Okay, so on quizzes and tests, I'm going to have you guys write it all out like this. And you just get faster at it, and you practice. Now, in Learning Hub, I have a number of examples where we go through. Now, remember, row 1 and row 2, these guys are going to keep the duet and octet rules. They're not going to exceed. Anything below that can, because they have access to d orbitals. Now, your job is to practice and do as many as you can and follow all of the steps. Don't do it in your head. I do not do it on my head. And I've been doing this way longer than you guys. And when you come into my office, I don't go, I draw it all out. And I will still always draw it because I make mistakes. And this helps me to make sure I don't do the mistakes. Now, let's see if I have a few of them here since we have just a moment. What I did, and we're going to draw a lot, and you guys are going to go on the boards next week, and you're going to be drawing them. And what I have done, I think it must have been in a separate file. In Learning Hub, I have drawn out a number of them with the steps. And I say, all right, how many valence electrons? And I show you. And I draw the skeletal structure. And I show you BPE. And then I show you the lone pairs. I show you remaining. And I do that for like 5 or 6 other molecules. So in your OWL homework, you're going to be tempted to look them up on the internet, ask Chat GPT, I don't know, or look ahead, and I don't do that. Now, the other challenge you're going to have is that there is a chemical drawing program in OWL, and that can be a little bit confusing on how to use. I do have a little tutorial video I'll try to include as I send that out to you guys. Okay? Otherwise, that's it. You are now gifted with the ability to write Lewis structures. Go and practice. I did my homework. I just forgot to write it down. Let's not be that guy. Let me know if you have questions or clarifications. We're going to run into some other issues next week, and it's all right. We're going to figure it out. This method works really well. Yeah, if you went to Spring Valley, you better have gotten this way. Otherwise, I'm getting after Mr. Zimmerman. And yeah.
So, first I have two questions. One about valence electrons, but first,
I'm going to turn that recording off in case you say something to incriminate yourself, or that I do.